What's up guys, and welcome back to another video. Today we're going to be deriving the differential area element in polar coordinates. In other words, we're going to be showing how the differential area dA is equal to r dr d theta. So let's first have a look at how we integrate things in Cartesian coordinates. So in Cartesian coordinates, we move along the x and we move along the y, and we create these tiny little areas, dA. You can take a small step to the right, dx, and a small step up, dy. And then we integrate these little areas. We add up these little areas, and as we take a limit, as dx and dy get infinitesimally small, this becomes an integral. So how is that different in polar coordinates? So in polar coordinates, we're also going to be increasing r and increasing theta by very small amounts, and creating boxes out of these and adding them all together. But here, there's a slight difference. In Cartesian, dx is a constant amount, dy is a constant amount, and all the boxes are the same size. So in polar coordinates, even though we move dr by a constant amount and d theta by a constant amount, we see that the boxes actually tend to get bigger and bigger as r increases. So from that we can note that we can start to see that there might be a dependence on r, how dA might actually equal r dr d theta. Let's now look at a close-up diagram to see exactly how this works out. So here I drew one of those little boxes. I'm just zooming it in so we can see it a little better. This point, let's call this r. This at a distance r and at an angle theta. And we're going to increase to get to this point right here. We're going to increase this angle by a tiny amount, d theta. And we're also going to move along by a tiny amount, dr. Now, what is the area of this box? Well, as we know from the arc length equation, S is equal to r theta, this length, this arc length right here, is going to be r times theta, and in this case it's going to be d theta. We know this is also moving by dr, so this is also dr. And this right here is going to also be r times theta, but the r is this time r plus dr, so we'll have r plus dr times d theta. And if we just distribute that, this is equal to r d theta plus dr d theta. But in the very, very small limit, this is going to approach 0 very, very quickly. So this might as well be 0. And in the limit, it will be 0. So, what is this area? Well, from this, we'll just get dA is equal to dr times r d theta. And since in polar coordinates, we almost always integrate r first and then integrate theta, we rewrite it as r dr d theta.